So, have you ever actually stopped to wonder how your computer, or even just the smartphone sitting in your pocket right now, manages to juggle so many things at once? I mean, you're streaming a high-definition video, downloading massive software updates, and running complex apps, all at the absolute same time, without the device even breaking a sweat. Well, welcome to this explainer. Today, we're going to unpack exactly how computers pull off this incredible high performance by breaking down the core mechanics of serial and parallel computing. To really get it, we're going to dive into the architectural heart of our machines. And don't worry if that sounds a bit dense. We're going to use a super simple everyday kitchen analogy to make all these complex engineering concepts crystal clear. All right, let's just quickly look at our roadmap for today. We're going to start by peeking inside the arithmetic logic unit, then we'll check out the limitations of serial processing, jump into the parallel computing revolution, look at matrix addition in parallel, and finally wrap up by optimizing a serial task into a parallel one. Let's get right into it. Section 1. Inside the arithmetic logic unit, or the ALU. To really understand how processing works, we've got to zoom all the way down to the micro level to see a single, simple operation. Now take a look at the precise flow of data happening here. Values are getting pulled from the RAM, which is basically the computer's main fast memory, and they're dropped into what we call registers A and B. Think of the RAM like your kitchen's main walk-in pantry, where you keep all your ingredients. Registers A and B, those are your active cutting boards right there on the countertop. The ingredients are then combined by the control unit operating the ALU, and the resulting sum gets dropped right into register C. That's your finished plated dish, right before it's saved back into the RAM. So the crucial takeaway here is that at its absolute most basic level, computing is literally just taking two inputs, performing one single logical step, and spitting out one output. If we stick to our kitchen analogy, the ALU is essentially a highly efficient kitchen appliance. Imagine a really good blender. You put two specific ingredients in, the blender processes them together, and you get exactly one blended output. It does this flawlessly, but, it can only do that one single task at a time. Section 2, Serial Processing Limitations. So what happens when things get more complicated? That single appliance works great for one quick smoothie, sure. But what happens when we string a whole bunch of those simple additions together into a much larger equation? In a serial processing model, solving a string of numbers like A through F requires 5 strict sequential stages. And notice this, each calculation cannot proceed or even start without the output from the previous step. We start with G1, adding 2 and 4 to get 6. But step 2 absolutely needs that 6 before it can add our next variable, C. It's exactly like having just one lone, stressed-out chef in a kitchen trying to cook a massive 5-course meal all by themselves. That chef cannot start roasting the chicken until the marinade is finished, and they can't make the marinade until the garlic is chopped. Every single task has to wait in a rigid line. You can probably hear how agonizingly labored that sounds. The inherent flaw of serial processing is that because steps must wait in line, your execution time just balloons as your data volume grows. As long as every step is waiting for the previous one, you're artificially capping your speed. Think about it. If our lone chef suddenly gets an order for 10 banquets instead of 1, the wait time doesn't just double, it scales up massively, leaving everyone waiting around hungry and frustrated. Section 3, the parallel computing revolution. It was time for a major rethink. To solve this massive data bottleneck, hardware architects couldn't just keep making that single processor slightly faster. They had to completely revolutionize the approach, which led us directly to parallel computing. Instead of forcing one processor to run a marathon sequentially, we divide the race up among a team of independent CPU cores, running all at exactly the same time. Returning to our restaurant, parallel computing means we finally hired a full kitchen brigade. So instead of one overwhelmed chef, we now have a head chef with a whole team of sous chefs. One sous chef is chopping the garlic, another is boiling the pasta water, and a third is searing the meat, all simultaneously. The overall meal is prepared in a fraction of the time, simply because the workload is distributed. Section 4, Matrix Addition in Parallel. Let's see how this actually works in practice with something a bit heavier. Let's look at a more complex data structure, like adding 3x3 matrices together. This is where the architecture really shines. Because every single element in a matrix calculation is entirely autonomous, we can fire off cores 1 through 9 simultaneously to handle their own specific tasks. As we can see here, cores 1, 5, and 9 are all active, handling their own independent sliver of the math. It's like prepping a massive banquet, where every single cooking station has its own dedicated chef, who doesn't need a single thing from the chef right next to them. And meanwhile, cores 10, 11, and 12, they're just sitting idle, taking a well-deserved break, waiting for more work to come down the line.
Section 5. Optimizing serial to parallel. Now, let's bring it all together.
How can we actually use this multi-core breakthrough to optimize that sluggish 5-step serial addition problem we looked at earlier? Well, this is where the magic of optimization happens. By breaking the linear problem into concurrent tasks, we just look for calculations that don't depend on each other. We can calculate independent pairs. X is a plus b, y is c plus d, and z is 5 plus 3. We can run these at the exact same time. Then, we take those subtotals and quickly combine them. G1 becomes x plus y, and our final g adds that to z to get our final 28. We basically took a single recipe and figured out how to assign different totally isolated prep steps to 3 different chefs at once. Notice the absolute beautiful choreography here. What previously took 5 agonizing sequential waiting periods in the ALU is beautifully collapsed. We have cores 1, 2, and 3 tackle that initial workload simultaneously. Core 1 gets 6, Core 2 gets 14, and Core 3 gets 8. Then, Core 1 steps up to act as the head chef, taking those prepped ingredients, recombining them into 20, and finalizing the dish at 28. We've drastically cut down the time it takes to serve the meal just by organizing our kitchen staff a little bit better. Ultimately, breaking down complex problems into independent, concurrent workloads is the absolute secret to unlocking modern multi-core hardware. Whether you're rendering a 3D movie or literally just opening a new tab in your web browser, parallel computing is the silent kitchen staff making it all happen instantly behind the scenes. Which kind of leaves us with a massive question. As artificial intelligence and massive datasets continue to explode at this totally unprecedented rate, just how many simultaneous tasks will tomorrow's processors need to juggle? And really, how big will our digital kitchen need to get to handle it all? Thanks so much for joining me on this explainer, and keep questioning how the world inside your computer really works.